Everybody, today we're going to look at our review for our third test. So let's share the screen. Let's take a look at that. This is in your news item for today. And so let's go up to the top here. You received this a couple of days ago. Let's take a look at the solutions here. So first off, the first question deals with removable discontinuities. So there are discontinuities whenever the denominator equals 0. So whatever x values make the denominator equal to 0, there's a discontinuity there. Remember, there are two types of discontinuities. There's a discontinuity that relates to a vertical asymptote, and there's a removable discontinuity. The removable discontinuity occurs when we can factor the denominator in the numerator and divide out the offending values. So if we first look at this denominator, it says x squared minus 5x plus 6. If we factor that, it's x minus 3 and x minus 2. Set the factors equal to 0 and solve for each, and we get x equal 2 and 3. Since the x minus 3 factor can be divided out, it's removable. So that means there's a hole in the graph at that point instead of an asymptote. Contrast this with number 2. Number 2 says find all vertical asymptotes. So vertical asymptote is when it's not removable. Okay, so back on up here, for this x minus 2, we couldn't remove it. We couldn't divide it out. So there's a vertical asymptote at x minus 2. Similarly, just like we did up here, we'll take the denominator, set it equal to 0, factor, and find the offending points, the points that make the denominator equal to 0. In this case, that's 1 and 6. Neither of these are removable because they don't match up with anything in the numerator. If we factored out the numerator, we get x minus 3 and x minus 4. These two factors, neither one of them will cancel out. So there are vertical asymptotes at both x equal 1 and x equals 6. For the horizontal asymptote, remember the horizontal asymptote, number 3. For the horizontal asymptote, we look at the degree of the numerator and denominator. In this first example, when the degrees of numerator and denominator are the same, then we look at the leading terms, so 3 and 2. That's our that's our horizontal asymptote at y equal 3 over 2. For the horizontal asymptote, when the degree of the numerator is smaller than the degree of the denominator, there's a horizontal asymptote at 0. When the degree of the numerator, we don't have an example of this, but when the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. When the degree of the numerator is exactly 1 more than the degree of the denominator, there's an oblique asymptote. Remember, an oblique asymptote is a slant asymptote. So for this example, the second example here, g of x equals 2x minus 5 over x cubed. The degree of the numerator is less than the degree of the denominator. So there's a horizontal asymptote at y equals 0. Find the inverse. Remember, the inverse is a 4-step process. Here we have 7x squared minus 6 for x greater than or equal to 0. Have to have that restriction to make sure it's 1 and 1. We add 6. Now, first off, let me start with the beginning. We change out of x to y, switch out the x and y's, add 6 to both sides, divide by 7, and then square root. And so we end up with f inverse equals the square root of x plus 6 over 7. When we have a rational expression, it's a little bit more tricky. Okay. We do the same process. We start with changing the f of x to y, switching the x and y, and then isolating the y. To do that for the rational, we multiply both sides by the denominator and get this, the x times the quantity 10y plus 6 equals 5y minus 3. Distribute the x and get 10xy plus 6x equals 5y minus 3. We're going to group the y's on one side and everything with no y on the other side. That gives us 10xy minus 5y equals 3 minus 6x. This should be minus there. Then we take and factor out the y and divide by 10x minus 5. You get minus 3 minus 6x divided by 10x minus 5. So f inverse of x is equal to a negative because I factored the negative out of the numerator, just put it in front. 3 plus 6x over 10x minus 5. For number 7, we have a compound interest problem. And I think that's pretty self-explanatory. For number 8, we're going to go 2 to the x minus 3. You're going to graph it on your graphing calculator and be able to identify the horizontal asymptote that's slid down. In this case, since we subtracted 3, the horizontal asymptote is slid down 3 units. Expanding logarithms using log rules. So we have a product of a log, x over y times y plus 3. So our first expansion is to write the natural log of x over y plus the natural log of y plus 3. Remember, the log of a product is the sum of the logs. Now we have this quotient of x over y. So the log of a quotient is a difference in the logs. So log of x minus log of y. Then we still have that plus natural log of y plus 3. I just group the pluses together, put the negative behind at the end, and we get this. Did you have to do that? Probably not. I just did that just to make it a little more complete. Expanding the log of 6x to the 4th over y. Again, we have a quotient. So we'll expand it as log of 6x to the 4th minus log of y. Inside of here, this 6x to the 4th, we have a product. So we'll take the log of 6 plus the log of x to the 4th minus the log of y. And then lastly, we have this exponent with the x to the 4th. So we bring that in front and put it as a multiple of log of x and write as log of 6 plus 4 log x minus log y. We're going to express this into a single log. So we have the log of 35 minus the log of 7 minus 2 log 5. So in this case, before I do anything, since these are both negative, I'll factor the negative out and write as log of 35 minus the quantity log 7 plus 2 log 5. Then I note that inside the parentheses, I have this coefficient, this multiple of 2. I'll move up and write it as a 5 squared. And so that gives us the log of 35 minus the quantity log 7 plus log 5 squared. Now log 5 squared is 25. When I take the 7 and multiply it with the 25 because it's a sum, we get 175. And so we end up with the log of 35 minus the log of 175, because that's 175 right there. Reducing the 35 over 75 gives us 1/5. And then if I want to really write this as a single log, I could leave it that way, but the log of 1 is always 0. So that's going to be 0 minus the log of 5. And so since it's a quotient, I'm subtracting 0 minus log of 5, give me minus log of 5. Then for b, we have the log base 3 of w plus 4 log base 3 of t minus 2 log base 3 of w. So I'm again going to deal with this number in front of the log first, move it up into the exponent position, and get t to the 4th here for the log base 3. Same thing with the 2. I'm going to move it into the exponent position and get log base 3 of w squared. Nothing else changed. Next, I'm going to look for addition. Every place there's addition, I'm going to write that as a single log. Okay, so there's addition right here. And so I'm going to write this as a single log of w times t to the 4th. So log base 3 of w times t to the 4th, right there. Okay, and then minus the log base 3 of w squared. And so then, since this is minus, we're going to write as a quotient, single log base 3 of the positive part over the negative part. Now note I have a w in the numerator and a w squared in the denominator, so I can reduce that and write it as log base 3 of t to the 4th over w. The change of base formula, again, is pretty self-explanatory. You should know how to use that. Either form gets you the same answer. The log base b of m is always the common log of m over the common log of the old base. If we use natural log, we have the natural log of m over the natural log of the previous base. Either way, when we plug log base 3 of 8 in and take log of 8 over log of 3, or the natural log of 8 over the natural log of 3, we get 1.8928 using 4 decimal places. Solving equations, we have several things to solve in this test. We have 2x2 systems, we have 3x3 systems, we have exponential equations and log equations. So with an exponential equation, the first thing you do is you isolate the base and the exponent. We already have that done. Once that's the case, you log both sides. So we log the 3 to the x plus 2 and log of 5. Now, if this was an e, I'd natural log. Otherwise, I'm just going to log. When I take the log, whether it's a natural log or common log or whatever log base, it means that if there's an exponent inside the log, this x plus 2, I can bring it down front and write it as the quantity x plus 2 in this case times log 3 equals log 5. I'm going to divide both sides by log 3. This gives us x plus 2 equals log 5 over log 3. Isolating the x, we subtract 2 from both sides and get log 5 over log 3 minus 2. Then we'll push this into our calculator. Log of 5 divided by log of 3, making sure we have a parenthesis after the 5 and a parenthesis after the 3. Minus 2 gives us approximately minus 0.5350 to 4 decimal places. Okay. I'm going to use the quadratic formula in B. I have a quadratic eventually, and I'm going to use the quadratic formula. I'm going to round the answer to 2 decimal places for B. So we take this log equation that we have here, log base 2 of x plus log base 2 of x minus 9 equals 3. We first write as a single log using log rules. Okay, we want to isolate the logs on one side and use a single log. So to do that, we have both logs on this side. We have addition between. So that means we're going to write a single log of the product x times x minus 9, that quantity, equals 3. So the single log base 2, distributing x now, gives us x squared minus 9x equals 3. We're going to rewrite as an exponent equation. So our base is 2, our exponent is 3, and it equals x squared minus 9x. So we have 2 to the third equals x squared minus 9x. Well, 2 to the third is 8. Since it's a quadratic equation, we'll subtract that 8 from both sides, getting x squared minus 9x minus 8 equals 0. Using the quadratic formula, we get x equals 9 plus and minus the square root of 113 over 2, which is approximately x equals 9.82 and minus 0.82. Now we should go back and check both numbers in the original equation to make sure that we're not taking the log of anything negative. So if I put positive 9.82 in for x, I'm going to take the log of a positive number here. If I put positive 9.82 in here, 9.82 minus 9 is 0.82. I have the log of a positive number. If I come over here and take the minus 0.82 and put it in here, I'm going to get minus 0.82 minus 9. That's going to be a negative number. That can't happen. Similarly, if I put the minus 0.82 in here, I'm going to take the log base 2 of minus 0.82. That's not defined either. So I have to throw away the minus 0.82. And I just mentioned it here as the first one, the log of x. We should be able to solve systems of equations a variety of ways. 2x2s we should be able to do by elimination and addition. We should probably be able to do a basic 3x3 as well, but I'm going to encourage you to use your row reduce echelon form feature of your calculator for these for right now. Okay. So for C, we have y equals minus 2x plus 5 as one equation, and minus 3x plus 5y equals 7 as the other. Okay. Since y is isolated here, I can take what x is equal to here, or what y is equal to here rather, the minus 2x plus 5, and substitute it in for y down here. And so our second equation becomes minus 3x plus 5 times the quantity minus 2x plus 5 equals 7. Solving this equation for x, we get x equals 18 over 13. Taking 18 over 13 and plugging it in for x into this first equation gives us minus 2 times 18 over 13 plus 5. Solving for y, that gives us 29 over 13. For d, I used elimination. So to eliminate, that literally means we eliminate one of the variables by adding the equations together. So I'm going to multiply the first equation by 2 and the second equation by 3. Why? Because that's going to give me a 6x in front of the x here and a minus 6x in front of the x here. 6x minus 6x added together give us no x. That eliminates the x. When we do that, we get minus 19y equals 57. Isolating the y gives us y equals minus 3. Now I'm going to take the y equal minus 3 and put it into the first equation to solve for x. This gives us 3x minus 5 times minus 3 equals 12. 3x plus 15 then, because of the minus 5 times minus 3, gives us 15 equals 12. Subtracting 15 from both sides gives us 3x equals minus 3, and x equals minus 1. For the last one, I want you to try to use your RREF feature. When you use your RREF feature, you should get x equal 3, y equal 2, and x equal 3. Hopefully this helps. Have a good day.